Hello everyone, myself Girish with basics of flow simulation, CFD and aerodynamics. So this content I have just gathered it from the internet. Okay, it's for educational purpose. Well, we'll see what and all the basics needed for fluid dynamics as a beginner. What is CFD? It's a computational fluid dynamics which will help us to deal with the simulation of fluid engineering systems by using modeling and the numerical methods. Okay, in numerical methods we can say first we'll discretize the model, and then we'll use the solvers and numerical parameters. By just doing the grid generation we'll get the outputs. Okay, there are two types of CFD analysis. One is AFD and EFD, that is analytical fluid dynamics and experimental fluid dynamics. So during 1947 we had 20 teraflops, and then during 2003 we have 1.3 pentaflops. Okay, so these are the computer resources, and then it keeps on increasing year by year. Why CFD is needed? Okay, so if you are going to analyze and design based on the like aerodynamics called as on ships and airplanes, like environmental effects like winds and weather, and if I consider hazards like explosions, radiations and pollutions. So in these all the criterias we do use the physical fluid phenomena. Okay, that time it is very difficult to deal with the experimental methods, so that time we use it. Okay, and then to get to know about the exploration of the flow physics, okay, to gather the knowledge about the how the flows will happen and what are the physics behind it, to just deal with these all the steps we use CFD. Okay, there are different subdomains as well, so like external flow analysis, internal, and even we can consider the HVAC analysis, and then if I consider electric cooling, and then comes with aerodynamics, like that is finding out the coefficient of lift and drag, and finding out the vorticity, turbulence. These all the things will come into account when you are dealing with the CFD. So before starting with the CFD, we need to know what exactly we need to do. First thing is to cross check the what exactly the objective is. So what we are looking for. So proof of the concept, the performance, and the engineering quantities. Okay, what should be known? The free stream conditions. Okay, and then geometry we need, and the configurations. Okay, what is the best analysis approach? What exactly we need to follow to deal with the analysis? Okay, first we need to check which type of flow it is, steady or unsteady, right? Is there any viscous effects into it, or whether the shocks will be present or not? So which type of equations we need to choose, iterative or something else? Okay, and what other flow models are needed? Okay, these are the things we need to consider. So here the simple example, that is practical testing, experimental testing, that is like wind tunnel testing. Okay, the airfoil section has been taken. With that we'll just cross check how exactly the aerodynamic quantities will change. Okay, that is lift and drag coefficients and static pressure distributions. This is a simple flowchart which will explain what exactly we'll go through the step-by-step process. The first thing is geometry, wherein we just select geometry and we'll define the geometric parameters. We'll simplify the geometry over there. And the domain shape, how should be the computational domain we need to select, and what is the size of it, and how much size we need to consider, and geometry conditions. Okay, coming to the physics, we'll cross check whether we need to include the heat transfer in solids or not. Okay, on or off, compressible or incompressible fluids, flow properties like turbulence or transition flow or supersonic flow, like this. With respect to Reynolds number, we can even vary. Okay, viscous or inviscid flow, boundary conditions, like what exactly the inlet and outlet flows are, what is the pressure at the outlet, like this. Okay, and initial conditions, few of the initial conditions like room temperature, what is the temperature of the fluid medium which you are taking into account, what is the initial velocity of it, these things. Coming to the mesh, there are two types. One is structured mesh and unstructured mesh, automatic and manual. Depending upon requirement, you can just mesh it. Solver, steady or unsteady iteration steps. Okay, convergent limits, so which value you want to converge, residual stress or question of lift or drag, like that we can consider. Precision, single or double precisions, this will be explained during the answer sessions, remember this one. Okay, then considering the outputs, we have the reports according to that, like xy plots and lift drag shear stress plots, and then verification plots and all. You can just plot it up once you get the results. Post processing, you can just use the contour plots, like temperature plot, velocity plot, pressure plots, like this. And even mass fractions and all, you can include the multiple contours actually. Now vectors, how exactly the flow is happening, where verticity is taking place, these things to find out, you can use the vector plots. Streamlines, how exactly the flow is happening. Okay, and by just visualizing the streamlines, we could able to just optimize the results or optimize the design by just cross checking the same. Okay, so this is the short explanation about the entire flow chart of the CFD process. Coming to the flow conditions and the fluid properties. So if I consider flow conditions, we need to know about the inviscid, viscous, laminar, turbulent flows as well. Okay, if I consider the fluid properties, we need to know the density of the fluid, viscosity, and the thermal conductivity of that particular fluid which we are considering. Next, the selection of models. So there might be different models available, so which model we need to choose. Okay, there are fixed codes available for that. And initial boundary conditions, like what exactly we need to define the initial conditions, that we all need to cross check these all the things. Okay, so which software also we need to use, that is also very important. There are so many softwares available in the market, which is the best one and which I need to choose with respect to costings. Okay, whether if I choose the multiple software, so if I choose the lowest cost software, whether it's gonna give the results with respect to higher software or not, like that we can cross check. But depending on the pricing, the standards, the capabilities will vary. But if you are looking into specific uh, condition, might be same everywhere, remember that. Yep, coming to the boundary conditions. So here you could see the inlet and outlet conditions we have defined. So with respect to that, if I consider inlet, there might be slip or there might be free conditions on walls. Okay, inlet, like velocity I can define, mass flow rate, and the constant pressure I can define as boundary conditions for inlet. Okay, and outlet, constant pressure, the numerical beach and zero gradients and all. And if you are considering the non-reflective components of the fluid, the compressible flows, and if you want to include the acoustics as well, so these things you can take into account. Okay, so this is the simple explanation. The viscosity effects, okay, and Reynolds number. So what exactly the Reynolds number, so why we use it, to just give the classifications in the flow, that is whether the flow is laminar or the turbulent or it is transition phase. How we can predict? By using the Reynolds number formula, that is rho v d by mu, where d is the diameter of the pipe, and u is the fluid velocity, rho v velocity. If I consider density of the fluid is rho, and mu is the viscosity, we can say dynamic viscosity. Okay, so you could see this is the viscous force and the Reynolds number. So if I consider Reynolds number less than 2000, we need to consider that as a laminar flow. If you're considering transition 2 to 4000 and turbulent more than 4000. Okay, so while defining the this parameter, we'll keep it automatic sometimes. If you know the Reynolds number, you can choose whichever you want. Okay, software is capable of now which exactly we need to choose. Coming to the speed of sound, we already know it is 343, that is 1234 kilometers per hour. So I'm weak with conversations. Speed which is equal to distance by time, this formula if I use, and then I can convert 2 meters per second to kilometers per hour. Remember these things. So speed of sound which is equal to 1 Mach. So the flows will be just measured in terms of subsonic, transition, supersonic flow, hypersonic flow, depending upon the Mach number. That is 1 Mach, which is equal to 1234 km per hour. Okay, 1234. Supersonic, we already seen. We have the aircrafts, fighter aircrafts. According to that, Tejas, if I consider, and then we have different aircrafts. According to that, the supersonic or hypersonic fighter aircrafts as well we have. Okay, so the classification, if I consider subsonic, it should be a 0.3 to 0.8, and transonic 0.8 to 1.2, and then if I consider supersonic 1.2 to 4 or 5 you can consider, or more than 5 it is hypersonic, or more than 4 it is hypersonic sometimes. Okay, uh, talking about coefficient of lift and coefficient of drag, so how you gonna calculate this one? So if I consider SolidWorks flow simulation, you will get the lift and drag force. According to that, you can formulate the equations to get the coefficient of lift and drag. Okay, the formula is coefficient of lift, which is equal to 2 times of lift divided by rho into v square into s, where s is the frontal area, not overall area. Very important factor, it needs to be remembered. Okay, if you are going to insert the equations dealing with this one, you need to remember the proper explanation for these all the terms. You could see here it is same thing. If I consider f of t, it is aerodynamic drag force. If it is coefficient of drag calculation. Okay, u is the velocity, you already know, and then the rho is the density of the fluid, and c is the drag coefficient. Okay, to calculate drag, if I implement the formula CD, which is equal to 4 times of GC into that is drag force, and then velocity square, this formula. Okay, fine. So this is all with this modeling. If I consider modeling, we need to cross check based on the physics of the fluid phenomenon. We'll just use the CFD to just categorize the same, that is viscous or inviscid. It is depending upon the RE. Okay, and then laminar and turbulent, Reynolds number again. Okay, external or internal flow, and then compressible, incompressible, a single or multi-phase, and free surface or surface tension is included or not, we need to cross check. Okay, chemical reactions and the combustions is taken place or not, these things we need to first check. So we'll have a few explanation about these all the terms. The Navier-Stokes equation, this is the entire equation, very important equation. Okay, it looks complex, but all the CFD modules will refer this one as a reference. The things are like, we gonna just utilize the continuity equation and the equation of states and the Rho equations to solve the safety equations. Okay, the viscous terms. So at this location, if it is viscous, so it will solve this equation. If I consider the pressure gradients, so anyway you're gonna deal with this one. Conduction, convection, and the radiation if it is considered, and this equation will be solved. And if you are going to take the local acceleration, so this will be into account. Okay, coming to viscosity. So we already know what exactly the viscosity is. If it is the resistance to the flow of any of the fluid over the another layer of the fluid. Okay, that is shear stress. If I consider shear stress, which is equal to shear uh, if I stress by strain, which is equal to let me just see the formula. If I consider this only, this is the dynamic viscosity, this is rate of change of velocity, right? So if I consider here it is shear strain he has taken, that is stress by strain, which is equal to dynamic viscosity formula. Okay, shear stress by shear strain is dynamic viscosity. Again, if you're considering the dynamic viscosity, the formula is this. Okay, and then for explanation you could see you can consider one stroke, what exactly the value is 0.001 meter square per seconds, and again few things. Kinematic viscosity of air and water is given here, 1.46 into 10 raised to minus 5, 1.14 into 10 raised to minus 6. You don't need to remember these all the steps, because anyway if you google it you'll get it. Okay, so if I consider the dynamic viscosity in poise, so it is equivalent to 0.1 pascal second. Okay, fine. So this is all about the viscosity. If I consider the specific heat, the amount of energy, okay, required to raise unit mass of a fluid for a unit raise in the temperature. Okay, so energy required to a mass, that is a unit mass of fluid, to raise the temperature of a unit, that is unit raise in temperature. If I consider any of the fluid, okay, the unit mass of that fluid, if you want to raise the temperature to a unit value, so that is known as the specific heat, the amount of energy. Okay, the raise in temperature might be T2 minus T1, or the T1 T2 we can consider the highest and lowest temperature. Okay, so this specific heat has the two extreme conditions with respect to the constant volume and with respect to constant pressure, Cp and Cv. So during engineering we had used these formulas to derive and these solve the equations and the problems related to the specific heat, that is Cp, which is equal to it is a Cp of air and Cv of air we have taken, that is Cp which is equal to 1.005 kilojoule per kg Kelvin, Cv which is equal to 0.8, that is 0.718. Okay, well, the speed of sound, so we already know, so according to that we can derive the equations. Okay, the isotropic process, that is C. Okay, speed of sound which is equal to square root of lambda into RT. Okay, coming to the relations for the gases and liquids, so this is the formula where the perfect gas light is P is equal to rho into RT. Yeah, you can refer this entire slide to just go through about this perfect gas laws and the expressions. Classifications of flows, we have the viscous and inviscid flow. Okay, depending upon the frictional effects we can consider the viscous or inviscid flow. Okay, and then coming to the internal and external flow, depending upon the internal and external boundary conditions, we'll just go through the same. Okay, if I consider the external flow, what exactly happens over there? The flow of any of the fluid is over the surface. Okay, if I consider internal flow, it is completely bounded inside a surface. Well, compressible and incompressible flow. So if I say any fluid or any flow which is compressible, if the density remains nearly constant throughout, okay, that is incompressible. If I consider any of the fluid which can be treated as a compressible, where the density variations will take place, okay, that might be more than 5%, okay. Well, laminar and turbulent flows, what exactly it is and how we're gonna cross check, okay. If the highly ordered flow motion characterized by the smooth layers of fluid called laminar flow. So I hope you have seen the effects of flow on the airfoil, okay. Depending upon the angle of attack, the flow will change to laminar to turbulent with transition phase as well, okay. For example, if I consider flow with highly viscous fluid at low velocities, okay, that is for laminar flow. Okay, what exactly happens with the turbulent flow? The statement you could see, the fluid motion that typically occurs at high velocities, okay, Mach number we can consider more than 2. There we can consider the turbulent effects, okay. You can take the airfoil or the circular tube into account, and you can start giving the like Mach numbers 1, 2, 3, 0.8, 0.4 and all. According to that you will get the turbulence inside the model, okay. So there even you can consider the Reynolds number factor. You can even change the Reynolds number to cross check the same, okay. Steady and unsteady flow, where there is no change in fluid properties, okay. If I consider steady flow, there shouldn't be any change in the fluid properties at the any point of time, okay. That implies the steady flow. Unsteady in the sense the flow properties will change with respect to time, okay. Remember that. So few of the questions for your knowledge. So what exactly the dynamic viscosity is? It is a ratio of the absolute velocity to the density of the liquid. So what exactly the difference between the uniform flow and the no uniform flow, that is non-uniform flow? If I consider flow should be uniform, okay, there the velocity and the hydrodynamic parameters will not change from point to point in any instant of time. That is uniform flow. The velocity won't change and the hydrodynamic properties also will not change. The non-uniform in the sense the velocity will also change, Reynolds number will change, according to that the hydrodynamic properties will also change, okay. Coming to the what is positive displacement pump? So what exactly it means, okay. These pumps are those pumps which operate by forcing a fixed volume of fluid from the inlet, okay. Then it will just what exactly it is, just a minute. These pumps are those operate by forcing a fixed volume of fluid from the inlet pressure, okay, inlet pressure suction of the pump into the discharge zone of the pump. Positive displacement. So these will take the fluid, fixed amount of volume fluid will be taken into the inlet with a certain pressure, okay, inlet pressure, and then thus will be discharged through the outlet. So these are known as the positive displacement pumps, okay. You can just Google it accordingly. And then what is the difference between the steady and unsteady flow? As I said, same uniform and non-uniform flow, same thing. The properties do not change with time. Here it changes. What is cavitation? Okay, the cavitation is the formation of the vapor bubbles, we can say vapor cavities in a liquid is known as cavitation. If you want to consider this one, we have the option to include the cavitation inside the CFD or not. the pumps, if I consider the pumps, which pump is more efficient, that is centrifugal or reciprocating, they will ask. So the answer is centrifugal pump, because the flow rate inside it is higher than the reciprocating pumps. Okay, the flow is smoother and again requires less space to install if I consider the centrifugal pump, and the lower investment cost and the maintenance cost. So how we can avoid the cavitation in the pump? First one, you can increase the pump size to a certain inches, so it will take a lot of time and the research and the development and manufacturing. Even you can consider the increase in the pressure of the suction head, decrease the speed of the pump. Okay, these are the three things you can do to just eliminate the cavitations. Okay, what is coefficient of contraction? It is the ratio of the jet at vena contracta to the area of the orifice. Why entropy decreases with increase in temperature? Okay, so we need to know what exactly the entropy is first. See, entropy is the measure of unavailable energy in a closed thermodynamic system. Okay, so this, if I consider, the formula will be there, that is entropy, which is equal to Kb into ln of rho, where Kb is the Boltzmann constant, and if I consider the rho, that is the number of microscopic configurations, and next the natural algorithm. So the ds by, that is discharge, ds, which is equal to dq by t, that is entropy is inversely proportional to the temperature. By just crossing this equation, we could able to know as temperature increases, entropy will decrease. If someone asks this question, we can simply counter by saying, okay, the temperature and the entropy are inversely proportional. When a real gas behaves like an ideal gas, when? So when we consider low pressure and the high temperature into condition, okay, into account. So what is continuity equation? So it is the mass conservation of, or mass conservation for a steady one-dimensional flow with one inlet and outlet. Continuity equation. Okay, here the mass conservation will takes place. So what is streamline and straight line? Sometimes this question plays a very important role. So every interviews this has been asked up to now. We have seen many of the interviews. So streamline is the line that is tangential to the instantaneous velocity direction. Okay, these are the tangential lines which showcase the instantaneous velocity directions. Straight lines is the line traced out by any of the particle of any of the fluid, we can say. Okay, Bernoulli's equation. So when streamlines are parallel, okay, when if I consider streamlines, if they are parallel, the pressure is constant across them. Okay, and then if I consider except for hydrostatic head difference, if we ignore the gravity, then the pressure over the inlet and outlet areas are constant. Okay, and then a1 v1, which is equal to e2 v2, you can consider this equation. Or if I consider the energy per unit volume before and after the flow, inlet and outlet, so it shows the equation, that is p1 plus 1 upon 2 rho into v1 square, okay, and rho gh1, which is equal to p2 into 1 upon 2 v2 square, velocity square, that is rho actually, okay, and then rho gh square. Okay, this is the formula Okay, if I consider in short what exactly the Bernoulli's effect is, okay, it is the reduction in the pressure which occurs when fluid speed increases. Okay, the Bernoulli's effect. Considering the geometry and the domain, okay, the simple geometries will be included like circular pipes and all. Complex geometries like airfoils and all we can consider. Okay, and then typical approaches by considering the geometry approximation and the cadency integration. If I consider, we need to take the standards, that is industry standards such as parasolid and step files and IGS files into account to just deal with this analysis. Okay, so there are different types of coordinate systems, that is Cartesian coordinates, cylindrical and the spherical coordinates. Okay, depending upon that we need to define the coordinates. Consider the turbulence and the free surface models. So turbulence flows will be, you already know, it is at high Reynolds number. Okay, involves the large and small scale sometimes. Okay, that is vertical structures and a very thin turbulent boundary layer near the wall. Okay, there will be a turbulent layer if I consider the boundary conditions. So turbulent models, there are DNS models and RANS models to predict the mean flow structure. Okay, and then LES, so which will help us to predict the accurate in separation regions. Okay, so it is quite expensive. If I consider a DES method where we'll take the RANs inside boundary layer and LES in separated regions. So RANs will help us to just predict the flow structure and LES will help us to just find out the separation regions. Okay. Numerical methods, there are different numerical methods we can consider, that is discretization method or solvers, and numerical parameters we consider grid generation transformation, and we can consider the post-processing with respect to high performance computation. Finite difference method, FDM. So in this we'll use the regular grids, okay, and the finite volumes and finite element methods to deal with the FDM. So mesh will be irregular, okay, usually. We gonna use the second order upwind scheme as well as the Taylor expansions to deal with this kind of FDM. And sometimes we can use the explicit method. So in explicit methods we can use that is Euler's method and Rangi-Kunta methods, or for implicit method we can use the V-Mommy method. Depends upon the requirement, we can just choose the explicit or implicit. Okay, if I consider again explicit here, we use the FDM conditionally, okay, where the time is restricted by the step. Okay, implicit methods are unconditionally stable but need more efforts on the efficiency. So again you could see a few of the things here: pre-processing conditions and stability and the selection of discretization methods. Okay, so if you want to consider the better answers or results or accuracy or the efficiency, we need to use the better mesh. Generation, so as you could see there are structured and unstructured meshes. Okay, the finite difference method will use the structured mesh into account. If I consider the FEM or the finite element, the structured or unstructured depending upon the accuracy required. Okay, so unstructured mesh will be used for more complex models where the results needed with more accuracy precision, we can use the unstructured grids. Okay, so like ANSYS Fluent will help you with that, and even we have different solvers in the market to deal with these. Okay, so these are the two different types of mesh. Structured usually hexahedral and unstructured usually tetrahedral. Remember that, they're very important terms. CFD codes, the Fluent, star CD, star CCM you can consider. And if I go ahead with the other CFD softwares like grid generation, they are grid Grambit and TechPlot and FieldView for the flow visualization. Okay, there are different softwares available, so these are the few explanation for that. CFD process, what exactly will happen, we already seen the flowchart. So there we use the geometries and then physics and then mesh it, solve it, report generation and the post-processing stages. Okay, and purpose we have seen already. CFD codes are as well we have seen. Okay, depending upon the flow conditions and the problems, we'll just go with the requirement. Coming to the density and the viscosity of the substances, that is air, water and honey, we have taken into account. Density of the air is 1.2 and the viscosity, and same for the water 1000 and remaining things. Okay, viscosity is the resistance to the flow of the fluid. It is measured in poise. Formula is given. Density, if I consider constant, if it is density is constant, incompressible. If it is variable, compressible. Okay, this is a mass momentum energy equation. If the momentum is, the mass conservation takes place here. Okay, continuity equation we can say that one. So this is the formula for that. If I consider the momentum conservation, that is momentum equation, this is, okay, this is momentum equation for the incompressible fluid. Finally, the solvers and the numerical parameters. Solvers include tridiagonal and pentagonal solvers. Okay, we can even consider the multi-grid solvers as well. Okay, solvers can be either direct, that is Cramer's rule and the gas elimination method, or we can consider even LU decomposition. If I consider iterative method, we'll take the Gauss-Seidel method into account and the Jacobian methods as well as SR. Okay, numerical parameters needs to be specified to the control calculations. So these are, so large, if you get the results, there we need to consider these residuals, like a change of results between the iterations. Let's say if I consider the CDCL, coefficient of lift and drag values, so how exactly it is changing with respect to iterations, whether they are like the results getting converged or not, we need to cross it, right? So precision, which requires single audible precisions, and the different numerical schemes which exactly we need to choose. These all the things will matter. The relaxation factor as well, and the convergence limit. So what exactly the uh, factor you're going to define there. So these all the things will contribute. Very important things to be considered while post processing. Okay, before solving the any of the CFD process. So this is a few explanation about the convergence studies. You can go ahead with this. And again, same thing. If I am gonna consider the monotonic convergence, you can use this uh, Richardson's extrapolation method. Okay, the correction factors we need to define, right? So few explanation about it. Yeah, so that's all about this session. You can refer this PPT anytime, which is made for educational purpose. I have gathered few of the things there. There are so many topics which need a better explanation. Okay, if you want to know about these all things, you can refer the aerodynamics textbooks, Anderson, as well as you can go ahead with the Googling. Yep, thank you all, stay tuned.